Hi, I'm Rio Futagawa. I'm part of the Robotics Institute Summer Scholars Program offered by CMU 2025 summer. I belong to the Air Lab under Dr. Sebastian Scherer, and I work on research project of informatic path planning. Today, I'd like to present the LLM-based semantics-aware prediction and planning. So, UAVs are increasing use in the modern world, such that on the right, UAVs conduct inspection tasks which human beings are hard to achieve, which increases the efficiencies of the industry that UAVs contribute to. Also on the left, UAVs contribute to exploration tasks in a cave-like environment, in this case, which is highly difficult environment where GPS cannot be used, and the drone relies on its pure perception to navigate itself through the cave. These missions were developed mainly through the DARPA Subterranean Challenge, which happened a couple of years ago, where the UAV focused on the exploration and inspection tasks through going through the caves. Through these missions, graph-based optimization methods were developed, and these are the prior knowledge of our research. So, as we dive into our motivation of our research, there are four main gaps that I'd like to fill out through this research. One, there's semantic prediction that has been used in these type of prediction and planning missions. However, the earlier researches lack in generalizability in a sense that it's compartment-based semantic prediction that is too restrictive. Also, recent developments in LLMs has attracted a lot of roboticists to apply LLMs into robotics research. However, LLMs have not yet been applied to semantic prediction in UAV inspection missions. Moreover, major exploration frameworks assume a global knowledge prior to inspecting such semantic location, in a sense that it's not an exploration and inspection task, it's rather pure exploration tasks or pure inspection tasks. Lastly, graph-based exploration, most of them ignore semantic patterns, where we would like to focus on. So the main gap in knowledge that we'd like to fill out is a predictive, semantic-driven planning, and an open irregular layouts using the LLMs. So, the main contribution of this paper is this process. Observation using perception. Sending the observed data, the local LLM, in our case, GPT-OSS. By sending the observed data of the semantic locations, we get back the semantic patterns in a mathematical equation, where we can use the mathematical equation to predict the location of the semantic nodes that we failed to observe in the initial round. Hence, we could see farther locations of the semantic prediction nodes, which we could use as a node to explore. Hence, the unified loop of exploration and inspection could be done at once. So, this is our system overview. First, we do the semantic detection. We send the roster node to the rosterama. Rosterama is a package which allows a local LLMs to be used as a roster package. We get the information of the predicted equations in a roster node. We use the roster node to construct a graph, which we solve a TSP-like path generation program, which we generate the waypoints to move around. Based on the generated waypoints, we use a basic exploration planner, which we aim to use the exploration planner, which the Air Lab developed for the Subterranean Challenge that I mentioned earlier. The exploration planner is very useful in a sense that it avoids the collision and moves around. So our goal, navigation, and also the path execution is done in this following logic. This is the online planning loop. First, we initialize. Initializing includes the perception, observation of the initial semantic nodes, change that into form and communicate that to LLM, get the ROS2 nodes back. Based on the ROS2 predicted semantic nodes information, we construct a graph. We plan as a formulated into an OpenTSP-like problem, which we solve online, with our aim to minimize the following, which is the total traveling distance. Minimizing the total traveling distance equals to minimizing the total traveling time. That means we're trying to improve the efficiencies to its maximum. As the UAV moves around, we acquire new semantic observations. We update the observed nodes when we compare the observed nodes data with the predicted nodes data. When we compare, if we fail to predict, but if we observe, we need to repredict and replan because the prediction was wrong. However, if we predicted, but if we couldn't observe, if we assume that the observation accuracy is 100%, our prediction was wrong, but observation didn't fail. In that case, we were predicting in a further area larger than the size of the observation target, in a sense that we could limit the domain of its predicted node locations, which we will remove the advanced prediction nodes and replan. Then the UAV goes to the next waypoint, and it goes through the circle. So the whole point of this is that most of the time, the UAV wouldn't replan or repredict. In this case, the reprediction and replanning, which are time consuming and also calculative and intensive, could be avoided most of the turns. So this is the example of our gazebo RBIS testing. As we could see, the draw on the left here is also the draw on the right in the red. As we can see, the left is the example of the structure that we'll be inspecting. However, draw on the right could be seen that it's only seeing or percepting the limited information. Based on this limited information, if we plug that into an LLM, we get the total image, total locations of the semantic prediction nodes that we need to inspect. In this case, which is the beams of this structure. Not limited to gazebo, we're also testing in ISAC-SIM. As we could see that our UAV simulator could move around the object, improve the we could inspect this around. So our future work is still there. We still have to do the real world testing and also the benchmarking to the current method, which I discussed earlier, which is a total exploration or semantic based exploration, which lack generalizability. We also like to extend the multi-drone systems to enable rapid and efficient coverage of large-scale environments. I would like to acknowledge special thanks to Ms. Rachel Burchin and Dr. John Dolan for organizing this for the summer. I would like to also thank Dr. Sebastian Scherer for advising me over the summer, and Dr. Mujin Kao for mainly mentoring me over the summer. I would also like to thank Jim Yuan and Sun Jin Pak for helping me out creating the program. I also like to thank other AirLab members for welcoming me to the AirLab environment. And I also like to thank the RISC 2025 cohort who are having a wonderful time over this summer. to acknowledgement. I'd like to say special thanks to Ms. Rachel Borgen and Dr. John Dolan for organizing the RIS 2025 and helping us get to CMU and, and conduct this wonderful experience over the summer. I'd like to thank Dr. Sebastian Scherer for advising me over the summer and Dr. Mujin Kao for mentoring me over the summer. I'd also like to thank Jibin Yuan and Shunjae Bak for helping me create the program. Also, I'd like to thank the airline members for welcoming me to a new environment. And thank you so much for the RIS 2025 cohort for the wonderful summer. Thank you so much. I'd like to say special thanks to Ms. Rachel Borgen and Dr. John Dolan for organizing the RIS 2025 and helping us get to CMU and conduct this wonderful experience over the summer. I'd like to thank Dr. Sebastian Scherer for advising me over the summer and Dr. Mujin Kao for mentoring me over the summer. I'd also like to thank Jibin Yuan and Shunjae Bak for helping me create the program. Also, I'd like to thank the airline members for welcoming me to a new environment. And thank you so much for the RIS 2025 cohort for the wonderful summer. Thank you so much.